Work and Energy. Part 1. Scientific Concept of Work. In this video, we will get an introduction to the scientific concept of work. Imagine you just completed your homework for the day and suddenly you hear someone say that you have not done any work. The term work has different meanings in our daily life and in science. What exactly do you think work is? Let's discuss some instances which we think of as work, but science considers it as work not done. You try to push a car, but the car does not move an inch. You might say that you have worked hard to displace the car, but according to science, no work is done here. Now, suppose you are rowing a boat or you are swimming in a river. In these cases, both you and science would consider it as work done. In our daily life, we consider both mental and physical effort as work, but science defines work quite differently. Earlier, we looked at a lot of activities that we consider as work in our daily life. Now, can you answer a few questions about those activities? Who is doing the work? What is the work being done on? What is happening to the object? Now, let's have a look at a situation that science considers as work. You kick a football. Your work is done as you are applying force on the ball and it is being displaced. In this situation, there are two conditions that need to be fulfilled for the work to be done. 1. There should be a force acting on the object. 2. The object must be displaced. If any of the two conditions are not met, work is not considered to be done according to science. Now, can you think of some situations from your daily life where work can be considered done according to science? Let us perform a simple activity and derive the mathematical formulae for work done. In this activity, we will consider the force acting on the object is in the direction of displacement of the object. Take a wooden block and place it on a table. Let a constant force F be applied on the wooden block. Let the wooden block displace through a distance S in the direction of force. Let the work done here be W. Here work done W is equal to force multiplied by displacement, which is equal to F multiplied by S. Therefore, work done on an object is equal to the magnitude of the force multiplied by the distance moved in the direction of force. Work has only magnitude and no direction. The SI unit of work is Newton meter, which is called joule. What do you think would be the total amount of work done when force applied is 0 or when the displacement of the object is 0? Do you think work done is always positive, or is there something like negative work? Now, let us consider some examples to see if the work done is always positive or not. Imagine there is a wooden block kept horizontally on a table and a string is attached to the block. Here, the displacement of the block is along the direction of the force applied. Now, we pull the string. The work done in this case would be force multiplied by displacement. In this situation, work done is positive. Suppose a car is moving from left to right with a uniform velocity. Now, we apply a retarding force in the opposite direction, that is, from right to left. There is a 180-degree angle between the direction of motion and the direction of force. In this situation, the work done is considered as negative. The work done may be F multiplied by minus S or minus F multiplied by S. Therefore, we can say work done can be negative or positive. Work done can be negative when the force acts opposite to the direction of displacement. And work done can be positive when the force acts along the direction of displacement. Now, take a look at this coolie carrying luggage. What do you think is the amount of work done by him against gravity? Here, the force acts perpendicular to the direction of displacement. In such cases, the work done is zero. In this video, we got an introduction to the scientific concept of work. In the next video, we will learn about kinetic energy. And energy. Part 2. Forms of energy. Kinetic energy. In the previous video, we got an introduction to the scientific concept of work. In this video, we will learn about kinetic energy. Try to remember the time when you were standing near the window and soaking in the warmth of the sun. That sun is the biggest natural source of energy available to humankind. Can you think of some examples of sources of energy from your daily life? We often use the term energy in our lives. But again, science has its own way of defining it. Let's look at a few instances to understand what energy is, according to science. Suppose you kicked a football and it rolled on the ground. Or you pushed a trolley and it displaced up to a certain distance. In both of these situations, the object has acquired capability to do work. And the capacity of an object to do work is termed as energy. The object which does the work loses energy, whereas the object on which work is being done gains energy. Suppose a ball A exerts a force on another ball B. On doing this, ball A transfers its energy to ball B. Then, after receiving the energy, the ball B possesses the capacity to do work. Therefore, we can say that any object that has energy can do work. Thus, energy is measured in terms of the capacity to do work. The SI unit of energy is that of work, which is joule. We can say 1 joule of energy is required to do 1 joule of work. Energy also has a larger unit, kilojoule. 1 kilojoule is equal to 1000 joule. The unit of work and energy is named after a British physicist, James Prescott Joule. He formulated the law of heating effect of electric current and verified the law of conservation of energy. Energy has various forms like kinetic energy, potential energy, heat energy, chemical energy, electrical energy, and light energy. Now, let's perform a simple experiment to understand kinetic energy. Take a heavy ball and drop it in a bed of dry or wet sand. First, drop the ball from a height of 25 cm. And then keep on increasing the height from where you drop the ball, like 50 cm, then 75 cm, then 1 meter, and so on. Don't forget to drop the ball at different positions each time, so that you can have a clear view of the depression in the sand. Now, observe the depressions and compare their depths. Which depression is the deepest and which is the shallowest? What led the ball to cause a deep or shallow depression in the sand? Now, let us find the answers to these questions by performing another experiment. Look at this setup in this picture. Here, a wooden block with fixed mass is placed at some distance from a trolley. Then, a known mass is kept on the pan to displace the trolley. Now, we will see that the trolley hits the wooden block and displaces it to a certain distance. Put a stop to the trolley after it hits the block and note the displacement of the block. The block displaced as it gained energy after work is done on it by the trolley. Can you tell from where does this energy come? Now repeat this experiment by increasing the mass on the pan. You will notice that with the increase in mass on the pan, the displacement of the block increases. It shows the increase in work done by the trolley. Trolley does work and so it possesses energy. The moving object is capable of doing work. A fast-moving object does more work than a relatively slow-moving object. Think of the rotating wheel or the bullet fired from a gun, both of which possess energy to do work. The energy possessed by the objects in motion is called kinetic energy. Therefore, kinetic energy can be defined as the energy possessed by an object by virtue of its motion. The more the speed, the more the kinetic energy. A speeding car, an athlete running, and a man swimming are a few more examples of kinetic energy. Now, let us have a look at the mathematical derivation of kinetic energy. Suppose an object with mass m is moving along with an uniform velocity u. Let a force F act on the object and it gets displaced through a distance s along the direction of force. Now, the work done W is equal to Fs. The work done on the object caused a change in velocity and it changed from u to v. Let the acceleration produced in the object be a. Remember, we studied the three equations of motion. And according to the third equation, v square minus u square is equal to 2as, from which we derived displacement. S is equal to v square minus u square the whole upon 2a. We also know F is equal to ma. Now, work done can be written as W is equal to m multiplied by a multiplied by s, which is equal to m multiplied by a multiplied by v square minus u square the whole upon 2a, which is equal to 1 upon 2m multiplied by v square minus u square. If the object was stationary when it started, that is u is equal to 0, W is equal to 1 upon 2 mv square. We learned that the work done by an object is the change in its kinetic energy. That is, if u is equal to 0, W is equal to 1 upon 2 mv square. Therefore, kinetic energy possessed by an object of mass m and moving with uniform velocity v is given by Ek is equal to 1 upon 2 mv square. In this video, we learned about kinetic energy. In the next video, we will learn about potential energy. Work and energy. Part 3. Forms of energy. Potential energy. In the previous video, we learned about kinetic energy. In this video, we will learn about potential energy. Now, let us have a look at some simple examples to understand potential energy. Hold a rubber band in one hand and pull the band with the other hand. The rubber band will get stretched. Now, release the rubber band from one end and you will see that the band returns to its original state. Why do you think the rubber band returned to its original state? It is because the band acquired energy when it was stretched. And this energy causes the rubber band to return to its original state. Now, take a toy car and wind it with its key. Then place the car on the ground and you will notice that the car starts moving. From where do you think the car got the energy to move? In all of the instances, the objects stored the energy from the work done on them. When an object doesn't use the energy transferred to it to cause any change in its speed or velocity, then it is stored by the object in the form of potential energy. You transfer the energy when you stretch the rubber band or wind up the key of the toy car. When you stretch the rubber band, the work done by you in stretching it is stored in it as potential energy. And when you wind up the key in the toy car, which compresses the spring inside it, the work done in compressing the spring is stored as its potential energy. Now, let us perform a few simple activities to understand potential energy. Take a ball and raise it to a certain height. The ball now has the capacity to do work. Then release the ball and you will notice that it begins to fall. Now, what do you think will happen if you drop the ball from a greater height? The ball that falls from a greater height will have a greater velocity when it reaches the ground. We did more work on the ball when we raised to a greater height. Thus, it possesses more energy. Now, take a bow and an arrow. Place the arrow on the bow with one end supported by the string. Now, stretch the string and release the arrow. You will notice that the arrow flies off to a certain distance. The bow stores the potential energy when the bowstring is stretched. And then this energy changes to the kinetic energy of the flying arrow. Now, let us understand what happens to the potential energy of an object when raised to a certain height. When an object is raised to a certain height, work is done on it by us against gravitational force, due to which an object possesses more energy when raised to a greater height. This energy possessed by the object is termed as gravitational potential energy. Gravitational potential energy is defined as the work done in raising an object from ground to a certain height against gravity. Now, let us derive the mathematical formulae for gravitational potential energy. Suppose an object with mass m is raised from the ground through a certain height h. The force required to raise the object is equal to the weight of the object, that is mg. The energy gained by the object is the work done on it. Let work done on the object against gravity be W. W is equal to force multiplied by displacement, which is equal to mg multiplied by h, which is equal to mgh. As the work done on the object against gravity is mgh, so the energy gained by the object is mgh, which is the potential energy of the object. Therefore, potential energy of the object EP is equal to mgh. When an object is raised to a certain height, then the work done on the object depends on the difference between the vertical heights of the initial position and final positions of the object, and not on the path taken by the object. Take a look at these two images, where two objects take two separate paths to reach from position A to position B. Here, AB is equal to h. In both the cases, the work done on both the objects is mgh. Now, do you know if energy can be converted from one form to another? There are various examples of energy conversion available in nature, like the water cycle or the process of photosynthesis, using which plants prepare food. Now, let us have a look at some examples of human activities that involve energy conversion. In the bow and arrow example we studied earlier, potential energy is stored when the bowstring is stretched, and it is used in the form of kinetic energy to throw off the arrow. Another example would be a running car, where chemical energy of the fuel is converted into mechanical energy, which aids the car to move. Now, can you give some examples of human activities that involve conversion of energy? Think about it. In this video, we learned about potential energy. In the next video, we will learn about the law of conservation of energy. Work and energy. Part 4. Law of conservation of energy. In the previous video, we learned about potential energy. In this video, we will learn about the law of conservation of energy. Earlier, we studied that energy can be transformed from one form to another, like the energy transformation in water cycle and in photosynthesis, or the examples of bow and arrow and a running car, which involves human activities to transform energy from one form to another. But do you know what happens to the total energy of the system before and after the transformation of energy? The total energy always remains the same, even when the energy is transformed from one form to another. This is known as the law of conservation of energy. The law of conservation of energy states that energy can neither be created nor destroyed. It can only be changed from one form to another. Law of conservation of energy is applicable in all situations and in all kinds of energy conversions. Now, let us perform a simple activity to understand the law of conservation of energy. Suppose a ball of mass m undergoes free fall from a height h. At the start of the fall, the potential energy of the ball is equal to mgh and the kinetic energy is equal to 0. Can you answer why the kinetic energy is 0 at the beginning? It is because the ball has no velocity in the beginning. Thus, the total energy of the ball is mgh. As the ball begins to fall, the potential energy is converted into kinetic energy. If the velocity of the ball at a given instance is v, then its kinetic energy is 1/2 mv square. When the ball continues to fall, the potential energy keeps on decreasing and the kinetic energy keeps on increasing. The summation of potential energy and kinetic energy of an object always remains constant at all points. Potential energy plus kinetic energy is equal to constant. mgh plus 1/2 mv square is equal to constant. The potential energy and kinetic energy of an object together forms the mechanical energy of the object. While the free falling of the ball, the amount of decrease in potential energy is the amount of increase in kinetic energy. Thus, there is a continuous transformation of gravitational potential energy to kinetic energy. Now, let us see if the total energy of an object always remains constant or not. Let us find out the kinetic energy, potential energy, and total mechanical energy of an object at two different heights. Suppose an object of mass 10 kilograms is dropped from a height of 5 meters. Take acceleration due to gravity as 10 meters per second square. Let's calculate the potential energy, kinetic energy, and total mechanical energy of the object when the height h is equal to 5 meters. Potential energy of the object, EP is equal to mgh, which is equal to 10 multiplied by 10 multiplied by 5, which is equal to 500 joule. Kinetic energy of the object, EK is equal to 1/2 mv square, which is equal to 1/2 multiplied by 10 multiplied by 0, which is equal to 0 joule. As studied earlier, mechanical energy is equal to EP plus EK. which is equal to 500 plus 0, which is equal to 500 joule. Now, let us calculate the potential energy, kinetic energy and total mechanical energy of the object when the object reaches the ground. And so, the height h is equal to 0 meter. Potential energy of the object EP is equal to mgh, which is equal to 10 multiplied by 10 multiplied by 0, which is equal to 0 joule. Kinetic energy of the object EK is equal to 1 upon 2 mv square. We know v square minus u square is equal to 2as. Here u is equal to 0. Therefore, v square is equal to 2as, which is equal to 2 multiplied by 10 multiplied by 5, which is equal to 100 meter square per second square. Substituting the value of v in Ek is equal to 1 upon 2 mv square. We get Ek is equal to 1 upon 2 multiplied by 10 multiplied by 100, which is equal to 500 joule. Mechanical energy is equal to 0 plus 500, which is equal to 500 joule. Now, on comparing the total energy of the object at both the heights, we will notice that the total energy remains the same. It shows that the sum of kinetic energy and potential energy is the same at the initial and final positions. Can you calculate the sum at other heights and fill up this table? Then we can see if the total mechanical energy remains constant throughout. In this video, we learned about the law of conservation of energy. In the next video, we will learn about power. Work and energy. Part 5. Power. In the previous video, we learned about the law of conservation of energy. In this video, we will learn about power. Do you think all human beings do their work at the same rate? Or all the machines consume and transfer energy at the same rate? The rate of doing work varies with all the individuals, and different machines also work at different rates. Now, let us have a look at a simple activity to understand how the rate of doing work varies for everyone. Suppose two athletes A and B decided to take part in a 100-meter race. Both are of the same age and have the same weight. A completed the race in 25 seconds and B completed the race in 20 seconds. What do you think is the work done by both A and B? Same work is done by both A and B, but B takes less time than A to complete the same work. Who do you think did more work per second? A stronger person can do a certain amount of work in a relatively less time. Similarly, a more powerful car can cover more distance in a short period of time than a less powerful car. These cars are classified according to their rate of doing work. And power measures this rate at which work is being done. Thus, power is defined as the rate of doing work, or the rate of transfer of energy. Now, let us look at the mathematical formula of power. Let the work done by an object be W in time t. Then, power is equal to work upon time. P is equal to W upon T. The SI unit of power is watt, which is denoted as W. The SI unit is named watt to honor the Scottish inventor James Watt. 1 watt is the power of an agent, which does work at the rate of 1 joule per second. 1 watt is equal to 1 joule upon 1 second. 1 watt is equal to 1 joule per second. Bigger unit of power is kilowatt, denoted as kW. 1 kilowatt is equal to 1000 watt, which is equal to 1000 joule per second. Power may vary with time. That is, the rate of doing work may be different at different time intervals. Thus, here the concept of average power becomes helpful. Average power is the total energy consumed divided by the total time taken. Remember, we studied about energy and its units. Now, let us learn about the commercial unit of energy. As joule is not enough to measure the larger quantities of energy, the commercial unit of energy is kilowatt hour. 1 kilowatt hour is the energy consumed in 1 hour at the rate of 1000 joule per second. 1 kilowatt hour is equal to 1 kilowatt multiplied by 1 hour, which is equal to 1000 watts multiplied by 3600 seconds, which is equal to 36 lakhs joule, which is equal to 3.6 multiplied by 10 raised to 6 joule. This unit is also used in our households. Let us take a simple example to understand the usage of the unit kilowatt hour. Take a look at the electricity meter in your house. Observe it closely. Take the readings of the meter at 6 AM and 6 PM for a few days. How much energy is consumed by your family during the daytime and during the night time? In this video, we learned about power.